I'm trying to get this. I did a video earlier today, it must be 12 hours ago, and it wasn't very long, it was about 30 minutes or something, 30 minutes I think it was, and it still hasn't been processed by YouTube. I don't know what's going on with YouTube just lately. It's just really crap. Hang on a minute, just trying to get this up. Right, I want to check my stream, because before I start I want to make sure it's working alright. So if you haven't seen the video I did, oh, it's there. Really crap. Hang on a minute. Just trying to get this up. Right, I want to check my stream. Just mute myself because I'll get feedback. Right, the video has just been processed. Apparently it's there. The title of the video is a raw test on incomplete solid state generator. Right, that one. Anyway, go and have a look at it. It's very interesting. I'll explain it in this one anyway. I'm going to go over some things, because at first I thought maybe I've made a mistake somewhere. Let me just check I've got a message or somewhere. Oh, I get so sick of this flipping spam. Blooming dating girls. Spam. I hate it. I mean, I need to take care of that because I'm not giving bloody porn and all that shit free advertising. It's going to get deleted. And how the hell do they manage to get highlighted comment? How the hell do they get these are I'm going to report it. Pornography or sexually explicit material. Report. Go by. I'm sick of that shit, I really am. Sorry about my language, but I am pig sick of all this crap on YouTube. YouTube bans videos, but they can't even take care of some flipping porn? Come on, YouTube. What is wrong with you? Ridiculous, it really is. Right, so as I explained, I'll just go over it in summary, summarise. This stupid shit. Right, just to summarise, the generator is by no means complete. I've got extremely lossy corners on here at the moment. The steel lamination intersections are very good, which I made out of loads of steel rods. If you watch the previous video you should see that. So that's part is between here and here, and they're very good coupling. I've also got good coupling from here all the way down to the side of my concentric magnet arrays with my actuator coils, but there is a flaw in the actuator coils which I'm going to sort out, and the improved version is this. I haven't finished putting it together yet. I've just made these today. Now I'll tell you a little story. When I was making these today, I tripped over the wire and I was having a bit of a dizzy spell. I literally fell out of my front door. I fell down 2 steps and I landed face down on the concrete, and I scraped my hands up. I've got 3 plasters on my hands because I was bleeding all over the place. Bruised my arm. I don't know if you can see it, it's more bruised there. You can't really see it with this light. Scraped my legs, I'm in the right state. So yeah, the thing is I do for science, whatever, as they say. So I'm a bit battered up. So anyway, I was making these today. The reason why I was doing it on the step is because I was using the grinder, and I was using my steel. I'll just give you a bit of a close up. So you can see that. I had to 3D print the plastic, the pink stuff. Then I had to file them and trim them and sandpaper them and acetone treat them. And so I decided it was such a nice sunny day, I decided to do it all on the doorstep. I had the grinder there, which is, I don't normally have it there, and that's why I tripped over, because I tripped over the frigging grinder lead. So I spent about, what, good 4 or 5 hours making these two pieces, and these are going to be replacing the inner core for the actuator, for the magnet arrays. The actual magnet arrays on the concentrics are on the outside, so basically the magnets are around there, around the perimeter, facing inwards, so that we don't have to fight against the flux, because the flux is at a 45-degree angle to the axis to which it's being deflected, because that's what's happening, it's basically being deflected. So obviously one pole is subtracted, another pole is deflected forwards. So anyway, I spent all day doing these, and they're not dry yet. So because they're not dry yet and they're acetone treated, they've swollen a little bit. The plastic tends to swell up a bit. So by tomorrow they should have shrunk enough. I've sandpapered these down a bit, and they're almost wanting to go in. These are the mini concentrics that go on the inside. They're almost wanting to go in, but they're a little bit tight. So I don't want to sandpaper them too much. I'll tell you why, because if I sandpaper them too much and this ring shrinks overnight, it'll be too big by tomorrow. So I thought, well, I'll leave it overnight, let this shrink, because it'll shrink from outside inwards a bit and the inside outwards a bit, because it just shrink. It swells up a bit with the acetone. So I've got to let these dry out before I can actually put them in. Otherwise I end up with things rattling about, like often happens. So I'm just going to put them in the fan to get some air. Now, I've got a bit of good news. I was doing some testing on the previous video, and I was measuring current on the input. Now I'm pulsing this system with 40 volts, but it's actually, that's the voltage before it's gone through the H bridge. The H bridge swings it negative positive, so it's actually 80 volts. But the actual input current on the low side, which is being stepped up across the room, which you can't see, it's right over there, I don't know if you can see it on my big power meter, but it's actually 200 milliamps. But 200 milliamps coming in at 16 volts, actually it's probably 14 volts actually, but that's stepped up in by this unit here, which steps the voltage up to 40 volts, and we say the current at 40 volts is 40 milliamps. So we're actually using 40 milliamps to drive this H-bridge circuit, which I designed a couple of years ago, which is this thing here. I don't want to pull any wires off, but anyway, I don't want to move it around. I'll break some. Anyway, so this thing is set. Oh, I turned my oscilloscope off as well. Hang on a minute. I'll put it back on. Well, I have to re-angle my camera because I don't know if you're able to see the scope when it comes up. Anyway, we'll see when it warms up. So we're using 50 milliamps with a 94 milliamp output load. When I flick this, watch what happens when I flick this from current to voltage. No change on the input. Absolutely no change at all. Right, the waveforms coming up on the oscilloscope that waveform, the yellow waveform, is actually the output from my H bridge now, because I swapped it around. And the output from the H bridge is being smoothed by two capacitors in parallel with the coils to tune it, the circuit, and this is the improvement I made from earlier today. So bear in mind that we have something like 70% losses in these corners, on each corner, because I haven't got proper laminations there, because I'm just using ball bearings in the corners. So one of these capacitors, I'll figure out which one, it doesn't matter because they're both in parallel. One capacitor is 1 microfarad, the other capacitor is 700 nanofarads, so that's 1.7 microfarads is in parallel with a mismatched set of coils on the drive circuit. So one set of coils is like a 3 ohm, 3.1 ohm or something. Each coil 3.2 ohm. The other coil is somewhere, I think I haven't measured it exactly, but it's a lot bigger. It's about 10 ohms, or it's 8 ohms or something. But anyway, there's 400 turns of wire on that one, and there's only about 250, maybe 300 turns on this other wire. So they're completely mismatched, but they're in parallel, because I can't wire them in series, because the weaker coil, the higher impedance coil, would get all the juice and the other one wouldn't get anything. So they're in parallel, and the H bridge is driving both these coils in sync. Now, and the output is this one coil, because I haven't finished building this thing yet, because this bobbin at the bottom hasn't even got any wire on it. I haven't even finished it. I've got to wire some coils to the output specifically for this, because these coils here, this coil that's on here right now, was wound from a choke. So it's not even, I didn't even design that coil for this. It was for my chokes, these chokes that I was making, conventional transformers. So the chokes have got an impedance, the DC impedance of the coils is 1.6 ohms. And I didn't count the turns, but it's 22 SWG wire, I think. I'll go have a look. Oh no, I've got my wire in the way. Let me just check. Oh no, what is this wire? 22 SWG, yeah. So it's 22 SWG wire on this, which is not ideal, because okay, I get decent current, but there's virtually no voltage to use for driving anything like LEDs, because I could probably drive an LED with it, but the voltage is a bit too low to drive much with anyway. But the interesting thing is the input current. If you look at that, now watch the oscilloscope as well, watch the waveform, and I'll flick it back to current on the load. The actual input current hasn't changed one iota. The waveform, you can see there's a slight nudge on the waveform. I'll flick it. Can you see it flick? There's a slight shift in the very slight shift in the time base. The waveform advances and retards very slightly, but there's no actual compression or expansion of the waveform. It actually moves to the left when I take the load off. It actually moves to the right when I put the load on. So that's a phase shift that's happening, not an amplitude change, but a phase shift, and that is extremely interesting. That's something I haven't really seen that until now. And the other interesting thing, everyone says, well, you've got to use a resistor for real power. Okay, here's a resistor. This resistor is I think it's 1. I forget what it is. Let's measure it. Let's take my meter out of circuit. Let's go to ohms. Right, we're going to measure this resistor. I don't know what it is. I think it's 1.8 ohms. This resistor, 1.8 ohms. So what I'm going to do is I'm going to put it directly across this coil to measure real power, as they call it. As my friend Zero Fossil Fuels would always advise. So I'm going to put this back on volts AC. I'm just going to put this resistor back in this. Stick it on the magnet. It will get lost. I need to plug this back in. So I'm going to leave this on volts so you can see the load resistor coming into play. Right, I'm hoping you can see that. I don't know if you can or not. I hope you can. Stupid meter. I don't even know if you were able to see it last time, but let's put some light on it. Right, I can't do this with one hand. Let me put the meter over here. Move this wire up the way. Right, you should be able to see that. Like a camera. Move the camera this way a bit. I'll put them. Hang on. Like that. Right, you should be able to see now. Let's see. I'm looking on the computer to make sure you can see it. I don't think you can. Better put a light at an angle. Actually, I've put on top of the generator. It shouldn't affect. Oh no, I can't because I can't get to the resistor. Put the resistor on. I'll try and hold it while I do this. Oh, this is fiddly. Right, if I connect the resistor with one hand, which is not easy, to the output, you'll see the voltage disappear and we can watch the current on the input on the waveform. So we're going to put this across the get it in the right place. You'll know it's there because the voltage will drop off to 0 probably. It should do. I can do this without pulling my wires out. Come on. Right, we're connected. Now the voltage is dropped to 0.5 of a volt, right, and input current hasn't changed, and the waveform is just hasn't changed one iota. So I'll do that. You can't see the meter when I'm doing this. Oh, I'll pull the wire off now. Hang on, my meter's come off. Right, everything's falling to bits here. Come back on. Oh, I see, the wire's got wrapped around here. Right, how can you see that anyway? So just, actually it'd be easier if I just connect it to the coil itself, because, right, let me just connect it directly to the coil. That's a lot easier. Right. Right. Come on. Right, the voltage dropped to 0.14. You can see a phase shift on the scope with a connected up. But the output, actually the current on the input goes down when there's a load. I don't know if you can see that on that ammeter there. When I connect this resistor, I'm trying to get my arm in without blocking the meter. I've just noticed I've been blocking the meter every time I do this. Try to do it with this hand. The reason I put the camera over there is because I want to get everything in, and I'm not going to move all my furniture around. Right, come on, connect. Right, shit, slipped again, damn it. Just push this together, it's coming apart. It's still not fixed together properly. Oh, I've got to manage to get the resistor just on the resistor. Right, can you see the current on the input? 50 milliamps. Oh, it's gone off. No. Stupid resistor. The legs are oxidised, that's what it is. These frigging legs are oxidised. It's an old resistor. Come on, get on. Right, connected. 0.14. The input current. Move my arm out of the way. Input current 40 milliamps. It's actually dropped. 40 milliamps on the input. Take it off. It's actually gone back to 50 milliamps. So I'm actually using less power and got a load on it, which is really interesting. So this is what I think they were talking about, reverse reverse lens, is it? Yeah. I didn't know the name, I didn't know there was a terminology going around about that but until recently, but yeah, reverse lens is what they call it. Anyway, interesting, if that's the case. But it's extremely inefficient because it's only producing 3 volts and obviously output current is really, well, what's that in? The output current is only 94 milliamps shorted, and we're obviously using more than that, because on the low side from 14 volts stepped up to 40 volts. So on the low side we're actually using 200 milliamps to drive everything. So we're actually using twice the current to drive the circuit right now. So plus this board, this circuit, the driver circuit is running on these batteries. Now if I don't connect this, the circuit stops. The only thing that's powering this circuit is these batteries. The batteries don't power anything else, because I wanted to keep this circuit, because it hasn't got CMOS chips on it, it's got a lot of TTL chips, standard TTL, and they tend to be a little bit greedy on power, so I wanted to keep that part separate. And the high voltage is coming in on these 2 wires directly to the MOSFETs, to the drain on the MOSFETs, and then it's been switched to the source output, which is down these 2 wires to the coils. So that's how that works. The only part that's being powered by the batteries is the chips and the oscillator and the TL419 TC4. I can't remember the chip number now. I'll tell you, I'm getting senile. Yeah. So anyway, the chip has got dead time. Yeah. What is that number? Because I keep forgetting the names of everything. What is it? I think I've got bleached off. I can't see it. It's on my schematic when I designed it. Can't read the damn chip even. It must have got. Oh, it's some of these Chinese that the writing fades on them quick for some reason. Chinese chips. So anyway, yeah, it was just, as I said, it was just a follow-up. Sorry if you can't see the meter. Actually, if I moved it a bit closer, you would see it. I don't know if that'll work. There's freaking lamps in the way now. If I put the oops, the wire's not long enough. This is not going to work, is it? I'm going to pull my wires off in a minute. No, yeah, you can see it work better, but it's too dark. The light's over there. Yeah. So anyway, I'll just do I'll video it later on my phone while I do another test. I'm looking at the delay on the computer and it's, yeah, that's no good. It's too, actually you could see it at one point. Can't be fighting about with that though. Yeah. Well, actually the light's on it there. Yeah, well, I don't know. So anyway, so when I put this resistor on, we have real power, load. Oh, actually, I've got the load on it already, and look at that. It's still pushing out 41 milliamps even with this resistor on it. Bloody hell. This resistor is 1.6 ohms, I think it was. And I've put it across the coil. And I'm still seeing 39 milliamps coming through. Wow, that resistor should be getting warm. Actually, it does feel a little bit warm. Yeah, so I don't know what else to say right now because I'm still fighting about with the updating these. Now I've got to get some coils laser cut for the corners and to replace them silly ball bearings which are in there at the moment, which you can see. I've got black and white ball bearings out of a mouse ball bearing, so it's a balance between light and dark. I'm just being movie theatrical now, light and dark. Yeah, well, my things got stuck. Right, so yeah, I decided to use 2 white mouse balls and 2 black mouse balls. I thought it looked kind of contrasting. It's kind of funny actually. But they're very magnetic, as you can see. But unfortunately they have quite a lot of losses. That actually affects the waveform as well. You can hear the tone change slightly. And it seems to work pretty well at 1.8 kilohertz. I did take some video earlier, but I found out what I forgot to mention earlier. I found out there's a dip. When you're adjusting the frequency and also the dead time and the pulse width, the combination between frequency and the pulse width of the pulses, which are evened out by these capacitors, are in parallel in the output because it looks like a normal sine almost, but it's not actually a normal sine because it's pulsing in a very narrow waveform. Now let me move the scope to my let me just move the scope to, where's my torch gone? Let's move the scope to the actual time base. Come off. Okay, come off. Right. Let's move it to the actual output, the driver section again, because it was on there earlier in the previous video. Which one was that? I'm going to have to bring that back up because it's too low. Too big. Right, there's the pulse for the positive cycle. These pulses are for the negative cycle, but the waveforms all point up because I think there's an invert somewhere in here where I can flip one round, but never mind. But the dead time is, the pulse width is 496 microseconds. The cyclic RMS on the drive circuit system is actually 4.4 volts, which is kind of weird because that's what we're actually getting on the output, more or less, which is weird because this input is the driver section. It's nothing to do with the input that's coming from the power supply, which is kind of coincidental, but yeah. So that's the waveform. I don't know how well it's coming out on my camera, I really don't. I've got low. I can't watch HD while I'm streaming because it uses too much CPU when I'm. So anyway, we're at actually it's at 3.52 volts, so it's not coincidental. Now let's switch back to current. Current, frequency, current, frequency. Virtually, well, there won't be a change because this is on the drive circuit. So yeah, we're on the drive circuit monitoring now. We're not actually on the coil, so it won't show any difference when I change it. But the input current is actually these steel washers, and there's a lot of steel washers in here. If I stick a few steel washers around the corners, that changes the resonant frequency though. That's the problem. It's actually gone down slightly because it would have to be retuned. Yeah, I'd have to retune it all. When you add more mass to the corners, it would affect the tuning, obviously, because of the resonant frequency. So, but it will improve the coupling. I just don't want to fart about sticking steel washers that are going to fall off and stick to the magnets anyway, because there's nothing to hold them in place. So anyway, I thought you'd find that interesting. I am. It's very interesting. I mean, I did have this kind of teaser situation. What was it? 3 years ago, when I built the bubbleator with the rotary discs on the side discs, like that other disc thing over there, and I called it the wobbleator. That's the one. So if you search for the wobbleator, you should find it on YouTube. Wobbleator, all one word. It used to wobble about side to side, but I had some interesting effects with that one as well, because I used the same concentrics, the same kind of coil arrangement, but it was not in a circle. It wasn't in a closed loop system, it was in a straight line. And I actually had a situation where at one point it would speed up when it was under load, but it was a bit erratic and it was very unstable. And I know why now. It's because the frequency was relative to the actual speed of the rotors, and obviously the frequency would change with the rotor speeding up, slowing down. You could never tune it right because it was all dependent on the speed of the rotors. So that's part of the reason why I decided to go back to the solid state stuff, because you just can't tune a rotary system very easily. You can't, unless it's a synchronous situation, but you just can't tune it because frequencies on rotary systems keep changing all the time. So you might tune it for say 5,000 RPM, but if you put it under load, and as soon as it starts to slow down and it drops to 4,000 RPM, 3,000 RPM, what you've done to try to optimize and tune it has all gone out the window. But with a solid state system, you're fixed to the frequency of the signal generator. So I mean, there's a lot of benefits with solid state. Yeah. Anyway, I'm not going to go on and on because I'm tired. I've been up all day. I've been making them things. I fell down my frigging steps. I'm all banged up. I've got blood all on my trousers. Well, don't know if you can see it, but it's gone dark now because it kind of oxidised, but I had blood all over the place. No, it wasn't that bad. It's just my finger was oozing. This one, it was oozing. I don't know, it might be time to change my plaster. I took all the skin off. Look at that. Oh, that's a white state, that one is. The skin's hanging off. I need to let the air get to it a bit, I think. Right mess that is. I'm going to let this, I can almost see the bone, not quite though. Now I'm going to take it off and let the air get to it a bit, because it's I've been washing my hands and it's all gone white with water. But at least it stopped bleeding now. Yeah. I'm surprised I've still got blood in me actually. I thought I didn't bleed anymore. So anyway, this ringing in my ears is getting on my nerves now. So I want to turn it off, because I'm going to get it early night or something. But it's really interesting. Oh yeah, there's one more thing I can show you. One more thing. Under load, temperature. If I measure the coil, 27.8. The output coil is 27.8 Celsius. The temperature of the room, if I just measure this board here, because it's very close to it, but it's not actually running. That board is not running, and that's at 25.5. So there is definitely power dissipating in this coil quite effectively, and considering it's 22 SWD wire, that's quite a bit of current being soaked up there. So that board, which is not doing anything, and my meter's probably higher because I had it in my hands. So I'm looking for background temperatures. The batteries are probably warm because that's they're 26.3. So this board, which is very close to this one, let's measure this transformer. 25.5. So that's a stable mass. This big transformer at the back of here, that's at 25.5, and this coil is 27.2. So there's about 27.4. There's actually 2 degrees difference on that output coil. The generator coils are definitely warmer. The generator coils, the 32. I just had 32 Celsius just then. Oh, it's 37. 36. The other one, 33. So that coil's doing more work than this one. And that one's at 34. Oops, it's come off now. 34. That one's at 34. This coil is again, they're about the same. 35. Now that one's a bit warmer than that one, I don't know. Hang on a minute. These clips might be in the way. Right, 33.7. 34. So that one's 34, that one's 33.7. So the higher impedance coil is actually getting warmer than the lower impedance coil, which means there's losses in the higher impedance coil, more losses there. Very interesting. Right. Alright, I'm definitely going to go now, because I run out of things to talk about. And we'll see you later.